Hello everyone. The name of the presentation is Improved Attacks on GIFT-64. In this presentation, we start with the motivation and contributions. Following that, we briefly recall some related preliminaries. Then, we introduce the automatic method for the search of distinguishers. After that, we will show the ways to select 12-round linear distinguisher and 13-round differential distinguishers respectively. Then we display the linear and differential attack results. At last, we will draw a conclusion. So let's start with the first part. GIFT is a lightweight block cipher motivated by present design strategy. Its comprehensive treatment on the linear layer and the S-box makes it one of the most energy-efficient ciphers as of today. Moreover, it has significantly reduced linear Hall effect. For the good performance in hardware and software implementations, GIFT acted as the underlying primitives of many lightweight designs of the ongoing NIST lightweight cryptography standardization project. When we investigate the security of GIFT-64, we find few works consider the security of the cipher regarding the linear attack. Apart from the study of the 9-round linear Hall effect in the design document, we found no linear attack result on GIFT-64. At the same time, the previous 20-round differential attack demanded the full code book. So, motivated by these observations, we aim at improved linear and differential attacks on the cipher. And we think this will promote a comprehensive perception of the sumness of GIFT-64. The contribution of this attack can be divided into 4 parts. Firstly, to facilitate the selection of linear distinguisher in the attack, we estimate expected linear potentials of all 12-round linear approximations, with dominating trio being the optimal ones. Then, in parallel to the work in the linear setting, we give rough estimations for probabilities of 2,392 differentials facilitating 20-round differential attack. Then, benefiting from the good performance of the newly detected distinguishers, we propose the first 19-round linear attack and the first 20-round differential attack without using the full code book. In the next part, we briefly recall some necessary preliminaries. GIFT-64 is one version of GIFT with a 64-bit block size. It is a 28-round SPN cipher and has a k-length of 128 bits. Each round of GIFT-64 consists of 3 steps. In the subcells operation, an invertible 4-bit S-box named as GS is applied to every nibble of the cipher state. Next, the perm bits operation performs a bit permutation operation on the cipher state. At last, the add round k operation includes adding the round k and the round constant. In this figure, we only illustrate the bits that should be XORed with the round k, as adding the round constants does not alter validities of attacks in the paper. The most important steps in differential and linear attacks are finding distinguishers exhibiting non-random cryptanalytic properties. In this work, we explored an automatic method based on Boolean satisfiability problem, or VC-SAT, to accomplish the search of differential and linear distinguishers. A set problem is satisfiable if there is an assignment of the Boolean values to variables so that the formula is evaluated to be true. So almost all existing set solvers accept Boolean formulas in conjunctive normal form as input. So the Boolean formula in question should be expressed as a conjunction of one or more Boolean constants, and each constraint is a disjunction of Boolean variables. In the following, we will take the search of differential distinguisher for GIFT-64 as an illustration for the automatic search, and the search in the linear setting can be implemented likewise. According to the functionality, the Boolean expressions in the set problem can be partitioned into two groups. The first group is used to track the differential propagation inside the cipher, as the subcells operation is a unique nonlinear operation of the cipher. So describing the differential propagation across the cipher comes down to the description of the S-box. We donate X and Y the input and output differences of the S-box. Since we should encode the information about the probability, so we introduce four Boolean variables, rho 0, rho 1, rho 2, and epsilon. Note that the entries in the differential distribution table of GS has 5 possible evaluations, which are 0, 2, 4, 6, and 16. So the differential probability P of a feasible propagation only has 4 choices. We create an assignment to establish the connection between the differential probability P and the 4 Boolean variables so that the opposite number of the binary logarithm of P equals rho 0 plus rho 1 plus rho 2 plus 0.415 multiply epsilon. Then with this assignment, we generate all valid values of the 12-bit vector X concatenate Y concatenate the 4 Boolean variables. After that, we find the set of Boolean expressions of the S-box with the off-the-shelf software Logic Friday. Then the second group of Boolean expressions characterize the differential probability of the trio, donate the auxiliary variables for the J's S-box in the S rounds as rho 0 ij, rho 1 ij, rho 2 ij, and epsilon ij. Suppose that we aim at R-round trios. In theory, giving a perspective rational value omega for the weight of the trio, the automatic method should fulfill the search of trios validating this inequality. However, as the set problem is oriented to binary variables, so we do not find a feasible method to interpret decimal arithmetics with Boolean expressions. So we rewrite the predictive value omega as omega I plus 0.415 multiply omega d. Omega I and omega d are two non-negative integers. Then we transform the original restriction into two inequalities oriented to integers. For now, this kind of inequalities oriented to integers can be converted into Boolean expressions with the sequential encoding method. Now, let's move on to the selection of 12-round linear distinguishers. The The selection of the linear distinguisher can be divided into three steps. In the first step, we determine the length of the linear distinguisher. Note that the maximum absolute value of the correlation for 13-round linear characteristic is 2 to the minus 34. Given the weak linear Hall effect of GIFT-64, we conjecture that there is no 13-round linear distinguisher actualizing a valid linear attack. So we managed to use 12-round linear approximation to launch key recovery attacks. Considering that GIFT-64 achieves the full diffusion after 3 rounds, we expect to append 3 and 4 rounds before and after the distinguisher respectively. Thus, our goal is to implement 19-round linear attack on GIFT-64. After determining the length of the distinguisher, we apply the set solver to exhaustively search for all 12-round linear trios with correlation being 2 to the minus 31 and obtain 5,120 trios in total. Then the next step is to evaluate the number of sub-k bits GSBL of all candidate linear trios. This figure demonstrates the distribution for the number of linear trios with distinct values of GSBL. A rough estimation indicates that all the 5,120 trios have the potentials to launch valid 19-round key recovery attacks. Then we move to the next step. Apart from the value of GSBL, the value of the expected linear potential ELP also affects the complexity of the attack. Thus, in the third step, we turn our attention to the ELP of the linear approximations containing the 5,120 trios. The ELP of the approximation is the quadratic sum of correlations for all characteristics belonging to it. Due to the considerable number of linear approximations for each candidate, we can only exhaustively search for all trios with correlation larger than 2 to the minus 40 and give approximate estimations for the ELP. This table shows the distribution for the number of linear approximations with different features. The experimental result enables us to narrow the range of candidate distinguishers to 32 linear approximations. If we aim at linear attacks with lower data requirements, the group of 16 linear approximation with ELP being 2 to the minus 61.607 and GSBL equals 101 is preferred. On the other hand, the group of 16 linear approximations with ELP being 2 to the minus 61.611 and GSBL equals 91 is suitable for linear attacks with lower data complexity. Since the value of ELP of these approximations do not have significant difference, we use the linear approximation L16 in the second group to realize the following 19-round linear attack. Now we show how to select differential distinguishers in the attack. Similarly to the case in the linear setting, since the maximum differential probability of 14 round trios only achieves 2 to the minus 68, we try to find 13 round distinguisher so that we can improve the previous differential attack. Like the previous 20 round attack with the full code book, we also expect to append 3 and 4 rounds before and after the distinguisher. Thus, our goal is implementing 20 round differential attack without using the full code book. After fixing the length of the distinguisher, the second step is to search for candidate differential distinguishers. As shown in the figure, in the searching phase, we first set the objective probability as a relatively high value and obtain candidate trios with the set solver. Then we check the possibility of using the trio at hand to launch a valid attack. If none of the existing trios actualize a feasible attack, we lower the objective probability in the automated search and repeat the above-mentioned procedures. The selection task terminates until we identify at least one proper distinguisher. In the test, we found 288 trios with probability being 2 to the minus 62, 5,184 trios with probability being 2 to the minus 63, and 6,272 trios with probability being 2 to the minus 63.415. However, when these trios are exploited to launch 20 round differential attacks, the time complexities go beyond 2 to the 128 for the extensively involved sub-K bits in the sub-K enumeration phase. So we lower the objective probability to 2 to the minus 64 and obtain 92,768 trios. In the third step, for each of the trios surviving in the second step, we analyze the number of sub-K bits GSBD involved in the sub-K enumeration phase of the differential attack. The result is shown in the figure. A rough investigation shows that the 3,096 trios with GSBD less than 112 are qualified for 20 round valid differential attacks. After controlling the time complexity of the attack, in the fourth step, we focus on the data complexity, which is affected by the probability of the distinguisher. Before evaluating the probability of the distinguisher, we notice that some of the 3,096 candidate trios share the same input and output differences, and the number of distinct differentials is 2,392. In order to obtain approximate evaluations for the probability of these differentials, we use the set solver to search for all differential trios within each differential, with probabilities being larger than 2 to the minus 71. The distribution for the number of differentials with distinct probabilities is listed in the table. With this result, we narrow the range of candidate distinguishers to the 32 differentials with probabilities being 2 to the 61.313. The 32 differentials can be divided into two groups according to the value of GSBD. The 16 differentials named as D0 to D15 satisfy GSBD equals 107, and the 16 differentials named as D16 to D31 validate GSBD equals 110. Note that the following 20-round differential attack relies on the differential D3. Now we look at the cryptanalytic results with the newly identified distinguishers. To improve the accuracy of the ELP of the distinguisher, we apply the set solver to exhaustively search for all trios with correlations being larger than 2 to the minus 46. The ELP of the linear approximation is still 2 to the minus 61.607. In the attack, we append 3 and 4 rounds before and after the linear distinguisher respectively. The time complexity of the attack is about 2 to the 127.11 19 round of encryptions. The data complexity is 2 to the 62.96 known plaintext. The memory complexity is roughly 2 to the 60, and the success probability is 60%. Given that the time complexity of the 19-round linear attack is larger than 2 to the 127, we claim that the success probability of the attack is 60%, and it cannot be improved by repeating the entire work, as the time complexity will go beyond 2 to the 128. Also, in the differential attack, to ensure the accuracy of the probability, we apply the set solver to implement a more thorough search for trios belonging to the differential. All trios with probability being more significant than 2 to the minus 92 are identified, and the probability of the differential is still 2 to the minus 61.313. Similarly, in the attack, we append 3 and 4 rounds before and after the distinguisher respectively. The time complexity of this attack is 2 to the 125.5. The data complexity is 2 to the 62.58 chosen plaintext. The memory complexity is roughly 2 to the 62.58, and the success probability is 70%. This table gives a summary of cryptanalytic results on GIFT-64 to date. Note that the 19-round linear attack in this work is the first linear attack result on the cipher, and we also give the first 20-round differential attack result using the full code book. Now we finish all the content in the paper and give a conclusion. In this work, we estimate ELP of 5,120 12-round linear approximations and the probabilities of 2,392 differentials facilitating linear and differential attacks respectively. Thanks to the good performance of the newly detected distinguishers, we propose the first 19-round linear attack and the first 20-round differential attack without using the full codebook for GIFT-64. Given the newly obtained results, we conjecture that the resistance of GIFT-64 against differential and linear attack do not have a significant gap. Also, we note that the attack results in this paper are far from threatening the security of GIFT-64. That's all for the presentation. Thank you for your attention.